Welcome to Hot Chips 29. Tutorial 1. P4 for Software-Defined Networks. Language and Hardware Implementation.
So today we are going to start off with some background on software-defined networking. As a part of that background, we'll also explain what P4 is, where it came from, what it's trying to accomplish. We'll then go and dive into P4, the data plane programming language. And this is going to be the bulk of the content today. So you'll learn about all the different aspects of P4, packets, parsing them, matching them, applying actions to them, quality of service, etc. We'll also have an overview of the P4 toolchain. Now this is actually an open source activity to go and develop the toolchain. So you'll be able to go and download the toolchain yourself, experiment with it, really get down into the details. As an example of several hardware implementations, this being hot chips, we felt it's appropriate to include this section. There are implementations on the Tofino chip, which is a switch chip that's designed for this more programmable way of doing networking. There's an FPGA implementation and also a network flow processor, as well as a SmartNIC containing the flow processor implementation. And we'll close the day or the half day by covering some future directions, pointers to research projects, invitations to collaborate with us, etc. So the presenters include a variety of industry luminaries. Our friends from Cisco, Xilinx, Barefoot, and I'm from Netronome. So let's go and look at software-defined networks very briefly as an introduction to what we're doing here today. We'll cover the different planes. Data plane, we already talked about, P4 being the data plane programming language. But there's also the control plane and the management plane to consider. How do they fit in with the data plane? What is software-defined networking? What is the essence of it? And we really try to boil down this to the very essence to ensure we keep that in mind. And then what are the issues that come about if we introduce programmability in the data plane? How does SDN need to change to accommodate this? So the standard telecommunications architecture that most of us are very familiar with has the three planes. The data plane is all about the packets and forwarding packets. And here protocols like Ethernet, IP, TCP, UDP, for the older ones among us, things like ATM come into play. So here it's very much about the day in the life of a packet. How is a packet entering an intelligent forwarding device? How is it parsed? Which protocols, header fields are there to be parsed? Is there any type of classification done? How is it done with an exact match, with rules? These rules can also be viewed as things like routes in the case of IP, where you decide using a routing table or using an Ethernet switcher's self-learning table how to forward. And then typically packets are forwarded maybe with some light modifications. So that's the kind of things that happen in the data plane in a network. The control plane is really not about an individual packet, but more about the nodes and the links, the network topology, how to reach different parts of the network. So using the control plane, this is orchestrated and communicated among the different nodes in the network. And in this case, you see one of those protocols listed there, typically being used as a way to converge in a distributed way on the view of the topology of the network, with every node learning from the other nodes what networks are behind each node, and then building up a picture of the entire network, building up a picture of which path to follow to get to a certain destination. Now, the traditional way of doing this is really just to, for every part of the network to know what is adjacent. What next hop do I need to take to get to a certain destination? So you want to go to YouTube and you want to watch a video of cats playing piano, and from your home network, it will know what is local to your home, what is the default route typically to get to anything other than that. From your company, if your company allows you to do these kind of things, watch funny videos. The company network will know about all the sites that are there in the company, and it will then also know how to reach the internet. And in this way, every router, every entity knows how to go next. The management plane here is really about further higher layers. We, in the beginning, before a switch gets started, it needs to be configured. There are aspects like downloading software that are done in the management part. There may be graphical interfaces to allow humans to manually provision paths in the network. There are protocols like SNMP that allow you to monitor the devices and see how many packets flowed through each port, how many packets took a certain path, etc. Now, traditionally, there's always been software involved in all of this. So a plane is always has some type of software in it. In the beginning, the routers that were used were actually just code running on something like a Unix server. And it's only over time that, due to performance reasons, folks decided we need a faster way of achieving network communication, and we're therefore going to put more of this into hardware. In the telecom world, the notions of network management, element management, provisioning an optical network, using software to do the path computation, all this is also already very well known and very well established. So this software can handle different kinds of traffic. It understands about the different data plane protocols, Ethernet, IP, sometimes TCP, etc. But the algorithms, because they operate at these different scales or levels of granularity, have different performance requirements. So for example, your data plane, the software that would operate on that, or the hardware that then implements those algorithms instead of the software, has to operate on every packet. And you're talking about tens or hundreds of millions of packets per second. The software that operates at the control plane has to operate whenever the view of the network changes. When a link goes down, then a message gets communicated in the distributed way to say, we need to follow a different path, a different port on a switch is now the next hop to be followed. And then on the management plane, it may be even less rapidly changing, where you may be instantiating a switch or having things initiated by humans, and therefore be at the time scale of what humans can act to or react to. So the programming languages would also vary quite widely here. For the data plane, since there's a very high performance need, you would typically have quite an efficient programming language, or even do it in hardware. At the control plane, there's also some performance concerns. So the control plane may be written in language like C, maybe Java, and the management plane, because these are more UI level human interactions timescales, could be things like scripting languages and toolkits with many levels of objects that are used to build these. So what is the picture here when it comes to software-defined networking? As I said, software's use in networking has been extensive for many decades. So what is the key thing that started with the term software-defined networking? The first one is it's very often associated with OpenFlow, where OpenFlow allowed software to program the forwarding tables in the switches quite directly. So there was an older standard called Forces, which also attempted to do this, but I think it really only became popular with OpenFlow. And OpenFlow then, because it allowed you to program these tables, had a model or an architecture in the P4 world, is a similar term, which defined the switch behavior, which said that the tables match packets in this way. You can define actions in this way, and everything is exposed directly like that. So instead of doing something like having a BGP protocol learn about the adjacencies and the routes, and then leaving it up to the implementation to decide exactly how to do that routing, how to combine that with concepts like VLANs or MAC addresses on the lower layers. This explicitly exposed all the tables, where you could define table number 0 is a interface type of table, where you map the physical interface and the VLAN tag to a logical interface. And table 1 is a table where you're going to put your routes. And some other tables, maybe you put access control lists. So you can do things more than just forwarding with OpenFlow. The more familiar usage of the term OpenFlow is really about the protocol that is used between the controller and the switch to actually manipulate the switch given this model. So within the bounds of the model, you may, for example, say, here is an entry for a table called a flow entry. And this flow entry should go and match these fields. It should go and apply these actions if the match succeeds. So in the picture here, OpenFlow would be the structure of that switch, the arrangement of the tables. But it would also be the southbound interface, which is between the controller and the switch, and exactly defining that protocol. The last main contribution of OpenFlow and SDN in the broader sense here was that it introduced the notion of logically centralized control. So that is the SDN controller in the picture. And as you can see, there's only one of them for the entire network. Maybe not for the entire world's network, but for the maybe entire enterprise. Or maybe for your home, if you have a large home with a lot of devices. And the key innovation of this is that we do not need the distributed converging of knowledge that we have with these distributed routing protocols. So it's quite complicated to go and design something that runs on all the nodes, that talks to all the other nodes, but just has limited information, and then over time converges, that every node has a picture of the whole network and can reach each other node. If you have almost like a central authority that in memory, in software, can go and have a whole view of a network and simply compute all the paths that are needed, you can converge much more quickly. You can do things that are more advanced, like load balancing, and more efficiently use each node because you can know exactly where traffic is going to go and therefore spread it out better over the network. So that's a big benefit to the SDN concept. It does create the issue of it potentially being a single point of failure. And that is why it's listed here as logically centralized. It may actually physically be distributed among a number of hardware platforms, and therefore be still highly available. So this was a wonderful idea. You also had the notion of a northbound interface and many control functions that can sit on top of the SDN controller. So if people talk about applications in the world of SDN, they often refer to these control applications rather than data plane applications. And they can do things like influence the path computation or request certain connectivity scenarios and basically request the provisioning of a network in a certain way. And because of these benefits, I would say SDN's been very successful in the data center. Many clouds are provisioned using SDN. They are very often also using virtual switches, where a virtual switch like Open vSwitch, OVS, is using OpenFlow to be provisioned. And in that area, because it's very simple to manage things, it's been very successful. In some large WANs, for example, Google, SDN is also used. It's not necessarily OpenFlow in that case, but still the concept of central computation and just downloading all the table entries to the forwarding devices, that still applies. But the issues that arise are, it never really took off other than the Open vSwitch, which is very prevalent as a interoperability layer, where you can have different switches from different vendors be easily replaced by each other. For example, some number the tables in different ways. Others do not allow the first table to look at these fields, but the second table can look at those fields, etc. And that actually led to, at the controller level, southbound interface proliferation, where you may have different flavors of OpenFlow. You may know which table numbers you can use with this switch versus that switch. But then, because you need to be flexible anyway and have some differentiation anyway, people introduced other protocols, netconf, JSON, RPC, XML, etc., etc. And all these other protocols necessitated, if you will, a driver layer in the SDN controller, where there are these different plugins that cope with the different switches. But that also caused a bit of a monoculture, where you may get, in theory, Open Daylight, which is a standard controller, but in practice, you get Acme Corporation's variant of it, called Moonlight, Sunlight, whatever, flavor of daylight, to go and encompass what they need on the switches to be done, but also what they need on the control functions. So the notion of a fixed controller and many different software options and interoperability between the control functions, that also didn't really occur. What's the most important for us today, though, is that the evolution of the data plane protocols was hampered somewhat by the fixed model here. So to some extent, one could change the data plane a bit in OpenFlow. You can rearrange how table lookups are done, but you have a fixed vocabulary. Things like Ethernet, MAC addresses, IP addresses, TCP ports, and those are the only fields that you can refer to. And there was a need to go and support more rapid evolution of the data plane protocols than was achievable with the OpenFlow way, with the standard defining those fields. So inter-protocol independence. With protocol independence, the original goal was really to get away from this last part and to say we have programs explicitly defining the data plane protocols. So you would explicitly define the parse tree in a language, and we'll see this a bit later today. But then people realized you could gain additional flexibility as well when it comes to the data path behavior. So in OpenFlow, maybe you can have a list of actions that are executed when things match. In this language, you can go and do arbitrary branching of kind of if-then-else decision trees. You can also go and put queuing in more different places. Queuing doesn't always have to be at egress. It can be in the middle of the pipeline. There are better provisions for managing global state, etc. So the picture overall is very similar to the previous picture in that the switch is still programmed with an SDN controller. There are still control functions north of the controller. The logically centralized concept, only one controller, that's still valid. But the actual behavior of the switch isn't merely governed by table entries. It's actually now expressed in a program and downloaded. So now there are some issues here that we need to solve as an industry because of this. So first of all, that southbound interface needs to be more flexible. We need to take into account that people can define their own data plane protocols. If they want to define IP version 8 instead of IP version 6, they can go and do that. If they define very complicated behaviors, the higher layers need to know about these behaviors and need to be modified to take advantage of that. So it's then also the layers above the SDN controller, for example, OpenStack, that would need to be modified to take this into account. Furthermore, there's new entities here, like the data path program, the programmer, how are these data path things compiled and downloaded. They have their own entire life cycle that needs to be coordinated with the life cycles of the other software. of the control and management software in the blue boxes there. So there's a lot more to be said about this. There's different places where one can put things like drivers or agents or plugins to go and accomplish this, to go and be the abstraction that hides away all the details of the protocols. Furthermore, the protocols themselves can be designed in different ways to be either very specific to the program and expose an interface specific to interacting with that program, or be a bit higher level and more abstract, and therefore be able to serve many different programs. But I think today we are mostly focused on the data plane, on the data path applications. Please do not hesitate to grab me during a break if you care about these wider issues of how these programs interact with the rest of the software-defined network. So with that, I'll hand over to our next speaker, who's going to delve into the P4 language itself. While we're waiting for him to come out, we can maybe take a few questions. The question is the security aspects of the protocols. That's a really excellent question. I think when you are talking about the traditional usage of SDN, where there is a single controller, that is also the trusted entity. And the assumption is then that that controller is really there to program the network correctly, and if it needs to download access controllers to go and enforce certain security policies, it is kind of the entity which manages that. And it can then mediate requests from the northbound interface and say, okay, you as a control function or application, you're not allowed to do these things. I'm gonna stop you doing that. And that way, this is a little bit easier in the traditional usage of SDN. When we actually have programs that are compiled and downloaded into the switches, the notion of ensuring that they don't introduce vulnerabilities and issues arises. So you do need to take that into account when you introduce this new entity of a data path program. I think there's then aspects around the integrity of that program itself. Do you sign the code? Do you only accept code that's been signed by a permitted programmer? But there's also the aspect of, can you use these things to improve the security in your network? So originally, people wanted to go down this path to be able to go and define new data plane protocols, but they can actually use this as a tool to react more quickly to security threats. So if you see a worm in your network going and propagating, you can quickly go and make a modification to the data path program and in order to try and stop it. So in summary, the introduction of the protocol independence adds new challenges for security, but it can also be a tool to improve security. Okay, any further comments? With that, let's delve into the P4 language.
K. Lee from Barefoot Networks. I'm working as a tech lead in the advanced application team. In the advanced application team, we are building non-traditional applications to help the networking, sometimes storage, and also compute user applications directly running on the switch data plane. So we are taking full advantage of the programmability of the data plane. With that, I was able to interact with very different, each and every stack of the company, starting from the bottom at the hardware, RTL designers or verification designers, and also compiler and driver team, etc. So although I'm a software engineer, I hope I'm a bit qualified to cover this language material and also the hardware material a little bit. So the language material, it has lots of slides. It was originally designed to be covered in about 2 hours. We have to condense them in about an hour. So what we are going to do is, instead of just dropping the slides in the actual material distributed to you guys in a USB disk, we try to hide some of the slides, and we may just skip some of the slides in the middle of presentation, so that we can still convey the design principles of the language, but the details still can be left in the USB stick so that you can reference. And then I will probably take some questions in the break time, so that we can cover a little bit of a Q&A. Sorry. So the concept of P4 has started in 2013, and the P4 represents programming protocol-independent packet processors. So the name was introduced in that year, and the concept has been published in a paper, and the first version of the draft was published in 2014. So we've been called that language as a P414, and it's been very widely adapted and then supported by different targets. Based on the experience we collected from those multi-year development and then implementations, the community has come up with a new version of the language called P416. So today we are going to cover most of the P416, not to add more confusion to you guys, without touching too much of a history of P414. Yep. Okay, so let me briefly cover some of the building blocks of the P416. In order to design a programming language, it's good to have abstract machine model that the language is interacting with. So there are several different breeds of switching or the networking machines, or the switching machines. So we introduced this protocol-independent switch architecture called PISA. So it starts with a parser, where the stream of bits, basically the packet headers, are injected into the system, and then the programmer declares which headers that this switch is supposed to digest and recognize, and in which order the headers should be formed in the packet. So this is basically a state machine that starts from the first header in the packet, and then goes through the state machine to go to the next header based on some information embedded in the current header, or maybe the next header, and then emits the parsed set of headers to the next stage, which is basically match action pipeline. So this match action pipeline is the core part of this programmable data plane. It is composed of a set of stages. Each stage has a set of homogeneous resources, starting from, for example, the bus, where the parsed headers are going throughout the pipeline, and SRAM for the exact matching tables, TCAM cluster or TCAM blocks for LPM tables, for example, and some ALUs so that you can execute whatever actions you want to take on the packet. So this is a pipeline of those stages. So from hardware point of view, each stage looks exactly alike. And then it has no information about what protocol this device will run on. At the end of the pipeline, we do have a deparser. It's doing the reverse function of the parsing. So it takes the processed version of the headers by the pipeline, from the pipeline, match action pipeline, and then the deparser serializes the headers so that it can be sent into the wire. And then the order between these components needs to be well defined in this architecture. So let me show one simple example how it works. So let's say we have a packet just arrived at the switch from the input port, and the parser will see a packet which has a set of headers and also payload. So the headers are parsed by the parser and then given to the first stage of the pipeline. And throughout the pipeline, the headers can be read, or new headers can be added, or some user-defined metadata can be attached to this header so that it can help the processing in the later stages. And it goes through the multiple stages of this pipeline for any number of processing that you want to do in these given resources. And once every processing is done, the final version of the headers are fed into the deparser, and then these are serialized into the wire. OK, so now let's take a look at very abstract model of the program you want to implement. So in your mind, you have a switch that should do L2 processing and IP version 4, version 6, and security ACL, access control list. So the so there is an order between these logical functions, L2 function, layer 4, version 4, and version 6. So layer 2 should come first, and version 4 and version 6, they are mutually exclusive. They don't really coexist in the same packet in user cases. So they are their relationship between is kind of parallel. And then all the packets, either version 4 or version 6, needs to be handled by the ACL module. So this is your program. And then the compiler will help you to put those logics and also match action units, the logics put into the hardware resources. For example, the first stage can be used to implement the Ethernet MAC address table, which is doing basically the layer 2 processing. And then the second and third stage can do version 4 and version 6 address tables. And the final stage can do ACL tables. So this is done by hardware. And then there are multiple ways to implement or realize the same program into the given set of target, depending on what version of compiler you are using or the size of each table, etc. So let's assume that now you want to add another module called MPLS. Then, given the size of the MPLS tables and also the dependency, the order between these modules, the compiler can decide to put MPLS tables in the second stage and version 6 tables in the third stage, and the remaining resources in the stage 2 and 3 for version 4 tables. So in this case, version 4 is requiring larger tables compared to version 6. And same for ACL. So again, the hardware is purely agnostic to what protocols and what headers that these given hardware resources will be used for. This is purely up to you as a programmer who defines the behavior of the switch, and then the compiler will help you to realize that behavior. P414 used to have just one given switch architecture model, which is quite typical for many switching devices in the data center. It consists of ingress pipeline and egress pipeline, and it has a traffic manager in between. So traffic manager is basically doing queuing, congestion control, or replication, or packet scheduling, etc. So this traffic manager is not programmable component. Of course, you can probably configure through the control plane through the CPU. But the interaction between the ingress pipeline and egress pipeline, and also ingress pipeline and this traffic manager has been pretty well defined. The problem with this P414 switch model is that the language is defined only for this model. So if your target has a different architecture, the language doesn't really fit. You cannot easily reuse the same P4 program defined for this architecture to another architecture, to different architecture, for example, which doesn't have maybe deparser or may have multiple deparsers, etc. So to handle this issue, P416 took a bit radical approach. So here we are trying to support as many architectures as possible. So here architecture is basically an interface between P4 programmer and then the target device that you are actually compiling the program down to. So the community develops all the, So the separation between the language and architecture helps the community to develop the language as smaller than before, because architecture components is outside of scope of the language. But still, the community has developed a bit of very essential components as a part of the core library. And each vendor, or the chipset vendor, supplies basically the architecture definitions, including the definition of multiple external components. For example, if you have a specialized checksum engine, or in case you have some SSL offloading engine as a part of your switching device, then it can be defined as an external library here. And also the generic architecture definitions, basically the interfaces are also provided by the vendor. So the combination of two enables you to write a program that can run on maybe multiple targets if all the different targets are sharing the same architecture. For example, in case of Barefoot, we are building one chip, but the chip can be configured in multiple different ways, so that a little bit of change, for example, the number of pipes can maybe change from 4 to 2 or 2 to 1 by concatenating the multiple pipes into longer pipes. So architecture-wise, they don't really look much different. So the same P4 program can directly run on the different configuration of the target. So you can still use the same program and send almost the same architecture definition. But if you want to port your program written on this specific architecture for another architecture, then you can still reuse some portion of the code, because you will see that many of the programs are modular. So the target is basically the embodiment of the specific hardware implementation, and architecture is the interface, and platform is the implementation of this architecture on the given target. So when you write your P4 program, you are basically interacting with the platform itself. Okay, so to define a language, we first start with the data types. There are multiple data types relevant to the data plane programming, like bit strings or headers, structures, and arrays. And also it supports basic operations, logical and comparison operators. And we do support different type of control components, like how do you define each table and what action it can take, and the control flow between those tables. And again, parser is a part of important part of the language, so that you can build this kind of special state machine, which looks different from how match action table works. And most importantly, the architecture description given by the vendor is specifying for example, the order between these components. For example, in this particular architecture, we have two parsers, the parser 1 and some match action tables, a pipeline, and another parser, another match action tables, and deparser. And then it also defines the interface between these components. You will see an example in the coming slides. Yep. And the architecture may also provide the architecture or the target-specific external libraries. For example, you may have a checksum 16 or a checksum 32, or any offloading engines your target may be able to support. Okay, so P4 supports two also basic data types, and also it has a number of derived data types. So let's start from the header, which is the core building blocks of this data plane. So you have an Ethernet header. Here, the destination and source MAC addresses are described as a 48-bit wide bit string, and either type is a 16-bit bit string. So when you say bit string, this is unsigned by default. And if you want to declare a signed integer, then you can use int. And the language also supports a variable length bit string, which can be useful for example, handling IP header options or TCP options. Any TLB formed header can be expressed using the var bit. So the derived type, as a derived type, the header is an ordered collection of those member fields. Here, the destination, source, and either type. Here, the order matters between them, and also they need to be byte aligned. And although it's not shown in this user P4 level definition, internally, each instance of header has additional bit telling whether this header is valid or not. So you can call something like whether is valid, or set valid, or unset valid. The kind of actions can be supported for header. Similarly, we also define a VLAN header here. And you can define a struct as an unordered collection of those members. In this case, I define my headers struct, which has the Ethernet, and the instance of the Ethernet header, and also the instance of the VLAN headers. But in my case, I want to do Q in Q, so which means that I need to have a stack of VLAN tags. So this expression is basically instantiating an array of VLAN tags, which has two members. And P4 also supports the type depth so that we can make your code more readable. So here you can define the MAC address as a 48-bit wide bit string, and then replace the bit 48 expression by MAC address type that you have just defined. And var bit, yes. So this is an example of the version 4 header, but as you may know, version 4 header has 20 bytes of fixed portion, and it may also optionally has option headers. So option headers are variable lengths, basically. So although the IETF standard may depict all the headers in just one diagram, in P4 you can actually define those sections in two different header definitions. Like IP version 4 _T is just defining or declaring the the fixed portion of the header, starting from the version bit down to the destination address. And you can separately define IP option headers as having a member of var bits. This can be quite useful when you want to differentiate the behavior of a switch whether the option is there or not. Okay, so far we have looked at the headers, and another derived type is the struct. And so similar to header, you can also define your own metadata. And there are two types of metadata. Metadata is, you can imagine this as a kind of just variables that you can define in your C or C++ language. But as a metadata, there are also two different subtypes: intrinsic metadata and programmer-defined metadata. So intrinsic metadata is a kind of control bits or control registers that even used to communicate as an interface between different architecture components. So in this example, you may have a port ID and then multicast group and queue ID as a way to communicate your forwarding decision to the architecture or the target system. So here, the parser takes some structure. So parser input is containing the ingress port and then some flag indicating whether the packet is the original packet or some resubmitted version of the packet. So in this case, this parser input T is an input control variable. So you cannot really change the values, but these are given by the platform to share the information intrinsic to this packet. And you can also take the similarly ingress input T intrinsic metadata as an input to your pipeline, which also has an ingress port and also ingress timestamp. And ingress output T is the control variables that you can set as a programmer as a way to communicate your intent to the next component coming after this, your stage. In this case, port number as a result of forwarding decision, and multicast group if you want to do multicast, and drop flag if you want to drop this packet, or the egress queue, which needs to be local to each port number. So in the code, you can also instantiate these variables and also initialize those variables directly in the code. So in this case, we have VLAN tag is defined at the bottom, and you can initialize the values for this header using this form. Here, the 3W2 means that this is the 3-bit wide, and the value is 2. And then you can also take this form like a 16W, meaning indicating the width of the field, and then 0x meaning 16-bit hex. If there is no 0x, meaning the decimal representation. And you can also define this kind of constant, declare the constants to make the code safer than just using the define preprocessor. Okay, so we covered the basics of the data types. So now let's take a look at the parser example. So again, what parser does is defined by you as a P4 programmer, because parser is a programmable portion of this specific architecture. But the interface, input and output interface to this parser is predefined by this architecture given by maybe the vendor. So here we have my headers as a structure that you have defined as a set of headers you want to support in this parser. And animation is not that great. Let me just skip through this. Okay, so let's just first take a look at the architecture. Here you have 3 inputs. The packet in, which is the predefined extern given by the architecture. So this represents the packet itself. It has a data and also a couple of actions that you can take. And you can also make your own metadata as an input to the parser. You don't really need to do it, but doing this can take if architecture allows, you can do this, because once the metadata are defined as a input variable, then this particular platform may initialize the metadata to 0. So you don't have to explicitly initialize your metadata. And the standard metadata, which is basically the intrinsic metadata we have seen before. So the ingress port ID is given as an input intrinsic metadata to the parser. So the parser will take whatever processing to parse the set of headers that I want to support in this switch. And then the processed headers are emitted as an output, and also the metadata, maybe modified version of metadata, is also outputted from the parser engine. So the parsers have 3 predefined states. The start state is a part of the parser. So whenever packet is injected into the parser block, it always starts from the start state. Then you have to populate what the start state needs to do. And you can go through the set of state machines, defining what should be the next header, etc. But as a result, it can take one of the two predefined exit states, which is accept and reject. If your parser program is happy with this packet, then you can just accept. If not, it can be rejected. So the accept state and reject state is not part of your parser program. It's just kind of indicating what is the next step after this parser block. So if it's rejected, one given architecture, it may be just simply dropped, or another architecture may allow this rejected packet to still go through the next coming match action pipeline with some special information about the rejection region, etc. Okay. So this is the example of the parser state machine. Here I implement this my parser as a kind of instance of the parser abstract class defined by the architecture. So architecture provides this abstract class, then you are implementing the actual logics of this abstract class. So my parser has a start state, which first extracts the Ethernet header, and then it transits to one of those next states based on the either type value. So this is a select statement that helps you to select the right next step, next state. Sorry. So you can take some mask operation so that you can look at only the selected bits of this either type. And these members of the select statement is ordered. So the topmost one is executed, evaluated first, and then downwards. So it's like a TCAM table. And the VLAN parser is doing almost the same thing, but it has a different construction like a next and last. And they are useful to parse through a stack of headers. Basically, next meaning that I'm going to move on to the next index of this VLAN array. And last meaning the location of VLAN tag I just recently parsed. So in this case, you extract the first VLAN tag and looking at the either type of the one that just parsed, and then branch to the next state. And it includes the VLAN tag, so it means that you have a loop. You can create a loop to parse this stack of headers. And version 4, let me just keep. One thing you can notice here is that in case of version 4, it extracts the version 4 header, and then looking at the length, if the length is less than 5, which means that it's not a legitimate packet, so the packet will be rejected. The 5, then accepted. And if it's more than 5, then you go to the next state that parses the options. Okay, this is the last slide for me, my portion. The lookahead is pretty powerful primitive. So the problem here is that when you determine what next state you need to transit, sometimes the information is contained in the current header you are just parsing. For example, either type is a good example. But another information may be needed, whether the next protocol, let me just show an example. Yeah. So in this case, we are first parsing MPLS. So after you are done with the MPLS parsing, then you may go to the payload, and then payload may have a IP version 4, and version 4 or version 6. So whether the next IP header is version 4 or version 6 is not indicated in this case MPLS header. So you need to kind of look ahead the next header to determine the version of the IP and then transit to the right next state. Okay, this is for my portion, and then next will be the match action pipeline that will be covered by Robert from Xilinx.
Thank you. Grab a better pointer. So as JK was talking about, you have the packet, you've entered the parser, and you've basically pulled off the header information that you're interested in. What I'm going to start talking about is the match action pipeline. So we have these headers, and now we want to do something interesting with them. In this section, the three main keywords that we're going to be covering are the control, the actions, and the tables. So the control, like the parser, is a top-level container. It's where we're going to be declaring all of our actions, implementing our programmable logic. If you're familiar with C, it's going to look pretty similar. Things will be moved around, but in effect, the statements and expressions will look very similar. So like the parser, the controls will be defined by the architecture that you have. There will be user-defined controls, like the headers that you're interested in, metadata that you want to be passing through all of this. But there could also be architecture-specific interfaces. So we'll cover those when we get to them. But this talk we're going to be going similar to the last part of this, where a bunch of examples. And to start this off, it's just going to be a simple reflector example. So what we want to do is take our Ethernet headers. We're going to swap the source and destination MAC address, or source and destination address, and then we're going to forward the packet back out the port that it came in. On the right over here, you can see our block. It will take in header and metadata, both defined by the user for their specific application. This is the data plane specific. It's predefined. It's what you're allowed to use to affect how the packet gets changed, or how the packet gets handled in the switch. So the declaration inside your P4 program will look something like this. Control, you can call it whatever you want. You have headers, metadata, and then this standard metadata that's defined by the V1 architecture. In the control block, you have two sections where you can do things. The first is at the top, you can make all your declarations. Here's where you're going to put things like your action statements, your tables. Since we're just doing a simple reflector, all we really need is a single variable declaration. And then the second section is the apply. Every control will have this. It's where you specify your order of operations. So in here, for this example, first thing we do is just swap the source and destination. Pretty simple. And then by affecting or writing to the standard metadata, we set the egress spec to the ingress port. Now, the question is, how does this actually get forwarded? So if you remember back on one slide in JK's portion, we have this traffic manager called the packet replication engine. This is the element that it's defined by the architecture, but you can't modify it yourself. So the P4 program that you write doesn't have any logical place for this. All it defines is the standard metadata, which is your way of controlling it. And you can kind of see some of the ports for stuff that you can do. So if you have multicast, if you want to clone things, resubmit it. For details on how all of this goes, you can kind of read the documentation. This is just going to be a higher level overview. But this is where you're writing your code, and you can write it over here as well. So making the example a little bit more complicated, we're still going to stick with this reflector, but we're going to write it in a slightly different way. And we're going to be pulling in the action statements that are supported by the control block. So action statements can be defined in two locations. They're not specific to the control itself. So architectures, say you want to define something like a drop function. We can define our drop port as whatever value we want. In this case, we define it as 511. And then we can supply an action that the P4 programmer can use to just drop this packet. So for the reflector example, we can define a single action that does the swapping. It takes two parameters, as you would expect. They're both marked in and out because we're going to be modifying both of them. Logic is with the temporary variable and the swap. And the second one is to just reflect the port back by modifying the standard metadata. This portion is all declared in the declaration section. Quick little facts about it. So expressions are pretty simple here. They're mostly just assignments, but if you're familiar with C, you have your additions, your subtractions, bitwise, Boolean operations. The language, the P4 language will define a division and modulo operator, but it's up to the switch to say whether or not they support it. So in the case of the V1 architecture, general division and modulo is not supported. If you can reduce it to something like shifting or bit masking in that, the compiler will be smart enough to simplify that down, but just in general, it's not supported in the V1 architecture. That's not to say all architectures can support it, though. Other things that you can do is slicing off specific bits, or you can concatenate these together as needed. So now that we have all of our declarations declared, it's time to write our algorithm. And so we do this inside the apply block again. We're going to make it a little bit more complicated. So when you're doing a reflector, we're swapping the source and destination. But it doesn't really make sense to have a source address that's going to, say, a multicast. So we can do a checkup here with an if statement. We check the flag for multicast, or yeah. If it's 1, instead of reflecting the packet, we'll just mark it to drop. So it uses this value, or it uses that action. Otherwise, we just call our swap and reflect. For a flavor of other things that we can do with actions, you have your headers. If you remember, they have a valid bit, so we can do things like insert new packets. The way that we do this, every header will have custom or special member functions to affect the valid bits. So setting valid will mark it to insert the packet if it's not already there. Setting invalid will mark it to be dropped. If you want to do specific operations, whether this specific header is in the packet, you can read off the is valid. This is just an example. You're setting an MPLS header to valid, assigning it its values. If you have a VLAN tag, if it's valid, you update the VLAN tag's ether type. Otherwise, you update the Ethernet type. But bit manipulation, I'm going to glance over this. It's just as you would expect. If you're familiar with some hardware languages, you can select most significant bit, least significant bit. Values can be on the left-hand side, right-hand side. Now, at this point, we've used controls and actions, and that really creates just a static data plane. As Johann mentioned, you have control. You have the control plane, and that has to have some path into your switch. And the way that we do this in P4 is with tables. So they're the second half, or the first half of the match action unit. And tables here we can define with two properties are required. One is the key that you want to match on, and the type of match that you want to do on that key. And then the next property will be the actions, a list of actions that it can support. Other things, depending upon the architecture, can be added. It's very common to see a size, a default action. It's going to obviously have a list of entries inside of it. These entries are going to tell the data plane what to do when your key matches on a certain value. So the entry has the key value, the match type. It's going to have at least an action that it should apply, but if you write your action in such a way that it's taking data from the control plane, you will also store that action data inside this table as well. This portion here will be written from the control plane. So having a look at what this does in action, you have your table. It's been instantiated on your switch. The control plane sends some data to it, sets a default action, some default action data if it's needed. When the packet comes through this control block, you will extract off the keys and values that you're interested to make up your lookup key. This goes into the table. It can have a hit or a miss. Depending on which one it does, it will either take the action from the table along with the data, or it'll take the default action. And this will go into an action execution unit. The action execution is going to be defined as an action statement. If you remember to the simple reflector value, we defined our parameters, and they all had a direction. So this is a little subtlety in the P4 language, and it can trip people up when they're first getting used to it. For these parameters, you don't have to define a direction to them. And when you don't define a direction, what it means is the data will be coming effectively from the control plane. It actually comes from the table, which is programmed by the control plane. So in this way, our action statements aren't limited to just control actions and data plane actions. You can have a combination depending on whether the input parameter has a direction or it does not have a direction. Now, your action codes have access to all the headers and metadata that were passed to the control block, and they can modify these values as needed. Just a quick overview. So this is kind of highlighting the point for the control plane and the data plane and the difference between who does what, just because it really is a point that tends to trip people up. Basically, the data plane is everything that you're going to be writing inside your P4 program. The key format that you're looking for, so the specific fields, the actions that you can possibly take, data that goes into those actions. The control plane is going to provide the intelligence, which would be the values that you can program at runtime. So an example of this, we can define our action for just L3 switching. Notice that there's no directions to any of these parameters. So they're all going to be coming from the control plane. And you can use them inside expressions as you would any other parameter. Define a couple of them. You can call, so if you remember, we had a mark to drop action from the last example. You can call actions from within actions. Now, the table declaration. So this example is going to show you what that would look like. Say you just wanted to write a L3 host table. You would define your key. You can have multiple values for the key. In this case, we're taking the destination address and some metadata from the ingress. We're marking them both as exact matches, so the keys have to be exactly what's inside the table. We provide our list of actions that the control plane can assign to this table. So when you start writing more complex P4 programs, you're going to have a bunch of actions, and not every table can access all of those actions. You provide it with the list, and if you try to give it in the control plane, if you try to give it an action that's not in this list, it should throw off an error. There is one extra one that wasn't defined on the last slide. It's the no action. This is, as you would expect, just a no op. It's defined inside the core of the language, so you always have you always have access to this. It's typically used as the default action as a fallback. Defined in the core. At the runtime, you will program the table, so you give it the key values, you give it the action that you're interested in, and the data that can go to these individual actions. I'm going to glance over these next couple of slides. They're basically going to look the same. The idea is you have exact matches. If you wanted to do a routing table, you can do a longest prefix match on the destination address from your IP. It looks pretty similar from the control plane. I mean, you have extra data that will be going in, but effectively from the P4 point of view, it's just a table object with a different keyword. If you need something a little bit more powerful than longest prefix match, you can also do ternary matching. And again, looks similar. So using these tables inside of a control block, you're going to have our two sections. We declare our actions, you declare the tables, and then inside the apply statement of the control, you can call your tables. Now, tables have a assumed method that is an apply statement as well. Can get a little confusing sometimes, but to apply the table, you just give it the table name, call the apply method. You don't have to call them one after the other. You can put if statements to call tables under certain conditions. One extra thing that you have, so we have these if statements to do branching. Tables will give you two special properties for their results. So you can also do branching based off of whether or not a table hit. So say you have your host table that's doing the exact match. You say, oh, if I don't find anything in here, if I get a miss, then apply my routing table. You can also go to the action level. So depending on the action that gets run, you can apply more tables or more actions, things like that. As part of the control flow, we do define exit and return statements. This will let you just stop execution inside of a given control block, or if you use exit, it'll stop the switch and return from that point. Quick overview of match types. So inside of the core language, we define only 3. These are the exact ternary and LPM. For the V1 architecture, which is the common architecture people first trying out P4 will be using, there's a couple of extra types, range and selector, that you can use. The documentation will tell you how both of them behave and how to program them. And this is really, from the language point of view, just abstract types. So other architectures can define them as they wish. Quick comment on the key expressions. It doesn't have to be specific fields. You can do any arbitrary expression you want to do in here. You can do bit slicing. You can do it on whether or not headers are valid, things like that. It's really up to you in the language point of view. Now, one feature that some architectures will support, and it's useful for debugging, or if you just have a table where you already know what the values are going to be and you don't really need a control interface, you can actually initialize the table inside your program. The next thing that I would like to talk about is deparsing. So we've gone through the parser, we pulled off our headers, we've gone through the match action pipelines, ingress and ingress, and we've updated things as we want them to be, and now we need to reassemble the headers back into the packet. So this is a pretty simple block. It's not declaring any new language keywords. It just reuses the control, but it will be signaled by a packet out object. And this packet out object will have an emit method, and to this method you can pass a header that you want. It will only insert the header if that header is marked valid. So this is where it comes into play if you use the set invalid or set valid field of your headers. And the reason we do this is we just don't want a bunch of if statements, because like IPv4 and IPv6, you can just put them one after the other. And if your packet's using IPv4, that'll get output. When it comes to IPv6, it's not valid, so it won't get output. And you can declare this for as deep as you want inside your packet. One simplification that we do provide inside the deparser, if you're very careful about how you define your header structs, and you put all of your headers in the order that you would like to have them output, you can make your deparser as simple as just emitting that struct itself. The next topic is geared a little bit more towards architectures, but it's the idea of externs. So P4 is a language. P4 is a language we wanted to be able to target a lot of different vendors. And the reality of the situation is that a lot of vendors are going to have things that are unique to them, their secret sauce, so to say. And it can be very different. And we want the language to be able to support, at least at some level, a lot of these functionalities. It is also something that we use to simplify the P4.14 language as we move to P4.16. So I think we had something like 70 keywords in P4.14, and a lot of these were really specialized things. So we were able to just define them in P4.16 as extern objects. Externs will basically be giving you an interface. You can read the documentation to see what they do. They'll be vendor specific. But if you're looking through the architecture description, you will, I guess, one other point to make about externs. So as a packet's going through the pipeline, you can have external objects that will maintain a state. So what that means is the packet comes through, it can think of like a register. You can read a value with this packet and write some new value to it. The next packet that comes through will be able to see that updated value. Externs are the only place I believe that you can do this inside the P4 language. Technically, tables are stateful objects, but you can't really write to them with the packets themselves. They're only updatable by the control plane. But when you come across an extern, it'll look something like this. This is taken from the P4.14 language. A counter was, you would declare an array of locations. The counter had a single method, which was to count. You could either count the size of the packet in bytes, or you could count the number of packets that you had individually. With this method, you would pass it an index. It has a enum type for what type of counter you want to use. Using it inside the language, you have your control. You would declare the counter. The array size, in this case, we're declaring it to use packets and bytes, or to keep track of packets and bytes. And once you have this declaration inside your control, you can use it either inside the action statements or inside the apply. Depending on the index, you will update individual locations. Two other externs that were pulled in from P4.14 were the meters. I'm running a little bit low on time, so I'm just glancing over these. This is basically used for flow control. It's declared in a similar manner. You have your constructor. You have an execute meter. It can return, packets and bytes. And the third one is a register, which gives you a read method and a write method. So assembling the whole program now, this is the deparser was the third component. You had your parser, your match action pipelines, and then the deparsers. And once we declare all of these, you're ready to have your final program. So it'll look something similar to this. You can include the core library. You include the architecture that you're targeting, V1 model in this case. You declare your specific types, constants. You declare all your parsers and control blocks. And then for your package, so it knows where each of these go, you will have a package name. We'll pass each of your parsers and controls to this package, and it will be called main. Main is a reserved keyword. And that's it. Last point before we go to a break. having these fixed control blocks, it may be a little bit limiting. Like maybe you want to have your own control definition. P4.16 is flexible enough to do this, so you can declare a control as you would like. This case just has headers and some L3 metadata. And then in one of these top-level controls that the architecture supports, you can call your new control, and it will apply those statements.
Good morning, everybody. See everybody trickling back in. They told me to go right ahead, and we will get through some of the P4 toolchain. Happy 23 and a half hours to the eclipse. Anybody excited about the eclipse? Anybody going north for that? I'm actually planning right after this conference, or right after my talk today, driving up north to Oregon. Hopefully get to see the total eclipse the first time. That'll be cool. All right, but that's not the topic today. So I'm going to be talking about several pieces of the P4 toolchain. In particular, I'm going to be talking about the open source pieces of the toolchain. These are all, as you see available, these are all available on GitHub. They're all Apache licensed. Very nice license if you want to take this and extend it for commercial use or for other open source uses. Later, we'll have other speakers talking about vendor-specific tool chains. There are vendor-specific P4 compilers for particular devices and FPGAs and ASICs. I'm not going to be talking about those. Those will be later speakers after myself. All right, so all this stuff is open source, and it's all intended for primarily for debugging and development of your P4 programs and checking their behavior, and they're not for high performance. They're really targeted at debugging. All right, so what's the basic workflow look like? So you've got your P4 program up here on the left, test.p4 in this case, and the main open source tool that I'll be focusing on several of these slides is known by a couple of different names. The GitHub repository is called Behavioral Model. The BMV2 that you see in this slide is BMV2 is for Behavioral Model version 2. There was a version 1 earlier. This is just the second take on it. They decided to re-architect it a bit. And then Simple Switch is the name of the executable that you'll run on the command line, Linux command line. So I'll say sometimes BMV2, sometimes Simple Switch. They're all the same thing in this context here. So you want to get your P4 program first, you need to compile it. There are multiple open source compilers in the GitHub repository. This mouthful here, P4C, BM2SS. The P4C is P4 compiler. The rest of it is specific, specifies which backend you're compiling for, basically. And so the BM2 is Behavioral Model version 2, and then SS is Simple Switch. So there's a few versions of these, but this is the one we'll focus on today. The output you get from this is, it's a JSON format file. JSON is an open standard for all kinds of data interchange. There's a particular schema that basically, if you look at this, you'll see a lot of names that are, it's a text file format, and it's a digested version of your P4 source code that is intended to be read by this Simple Switch program. So you feed that compiled file into the Simple Switch executable. We saw earlier talking about there's a parser, ingress, match action pipeline, the packet replication engine / queuing and buffers is all in there, all modeled inside of here. There's egress match action pipeline and a deparser, and then a connection to Ethernet ports. Let's see. There's also a TCP connection. It listens on a socket for a connection from a control plane. The one I'll be talking about today is called Simple Switch CLI. Comes again with the behavioral model GitHub repository inside of there. And this is basically just meant for hacking. You want to add a single table entry to a table, you just give the name of the table and what key you want to match on. If it's a prefix, there's a prefix length, what action name you want in your P4 program, all the parameters that are in that action. You just specify in the command line. There's logging capabilities. Primarily, I'll talk more about those a little bit later. You can hook these, the Simple Switch, you can run it on a machine and configure it to connect to physical Ethernet interfaces on a physical Linux host. You can, but very commonly, you'll create virtual Ethernet interfaces, and I'll talk a little bit, show that later. And then you'll want to have some form of way of generating packet traffic for this. if it's, and then you'll want to be able to observe packets coming out. So there's a later slides that go through some of these steps in more detail. I'm going to just get the overview here. And there is a P4 debugger that you can do single stepping and looking at state along the way. I won't be talking about that one today, but just know that that one exists if you're interested in it, those kind of capabilities. Okay, so that's the overview. Let's go back and do a little bit more detail in each of these steps. So let's see, again, the command line for the compiler, this is the simplest, shortest step of all. The main weirdness is the name of the command. You'll just need to remember what the alphabet soup looks like. All right, so I've talked about this before. Again, the JSON format file is just a digested version, text file format. You can look at it and you'll probably recognize all the names that you see in your program. Then there's a script that is included in the open source tools for creating a set of virtual Ethernet interfaces, assuming that that's a reasonable thing to start with. You don't need to, it's easier to set up without having to go into the lab and hook up all the physical Ethernet interfaces of your device. So there's a script that comes with, there's several tutorial repositories. The behavioral model repository itself also contains one of these VE setup shell scripts that will create the virtual Ethernets. I'm going to quickly jump through these things because there's a lot of little fiddly options when you're creating virtual Ethernet interfaces, what kind of options you want them to enable or disable on them. Typically, if you don't do anything special, you'll get IPv6 neighbor discovery and other protocol packets running on the interfaces from the Linux kernel. And so turning those off can be nice. It's kind of noisy if you're, they can distract from your packets if you say they can see things flying across that you didn't send intentionally. All right, so the next step would be to start up the simple switch process. In order to generate packets using a raw interface on virtual Ethernet or physical Ethernet interface, it needs to run as root. So that's what the sudo command is there at the beginning. And there's a host of command line options for the simple switch. I'm going to show one example one, but obviously you can look at the documentation and see many others. So when you start up simple switch, again, it creates a model of all of these pieces. When you first start it up, before you've given it your compiled JSON file from your P4 program, it doesn't emulate anything. You can send it packets and it will just drop them on the floor. It doesn't know what to do with the packets until you've given it your compiled version of your P4 program, but it's ready to accept the compiled version of any P4 program, not just one in particular. So you feed that in by giving it an appropriate command line option, which is coming up here in a moment. Let's see. There are other options there that you also map. When you start it up, you can choose, I want to have 4 ports in my virtual switch that I'm emulating right now, or I want to have 20 ports. You can create as many virtual Ethernets or as few as you want, and then you can specify which port numbers, usually numbered from 0 on up consecutively, that you want to map to which Ethernet, physical or virtual Ethernet interface, and you can specify that on the command line as well. And there's some command line options shown with that. Logging to the console is a common option. You get to see lots of debugging information that appears as your P4 program is running. And then it will start, after it's loaded in your P4 program, in the form of the JSON file, it will then open up a socket and start listening for control commands. All right. Let me see. Oh. And then another option you can give, again, there are many options for logging. One is just logging to the console. You can log to a file. Those are text logging options. You can, this PCAP option that's shown here lets you, every packet that comes in or out of the emulator will get recorded to a PCAP file, which you can then, there's a lot of tools for, PCAP is a common standard file format for recording contents of packet captures. So you can, there's tools, open source tools like Wireshark, formerly known as Ethereal years back, and many other open source tools that can read and write PCAP format files. Wireshark is very nice for decoding and showing you the decode of all the headers in your packets, breaking them out by field names. Okay, so we've got all those pieces running. We've created the virtual Ethernet interfaces. We've started a simple switch after we compiled the program. It's waiting on that control socket. We could send it packets, but when you first start up the program like this, all of your tables, your P4 tables that you've defined in your program, will initially be empty. And so every time a packet comes in, it'll hit your first, it'll go through your ingress control block code, and it will hit the first table if you define one, and it will miss because that table will be completely empty. And so you can define a default action people often define a default action as maybe drop the packet, maybe don't do anything, do a no-op. So your program typically won't do anything very interesting until you've first installed some table entries into it. So you can definitely send packets, but you probably won't be very impressed with the behavior of it there. So before you want to do that, you typically want to attach some kind of control plane to this socket connection to start adding table entries. So there's much more complex things I'll talk about later, but for this case, we're just talking about getting your first program up and running and hacking on it. So Simple Switch CLI is a great choice for that, nice and simple. A nice convenience that they've added is when you start up Simple Switch, it connects to a default TCP port number. I think it's 9090 that it's the default listening port and the default connection port. You can fire up multiple Simple Switch processes on a single host, and then you just have to give non-default TCP port numbers on the command line so they don't conflict with each other. But if you're only starting up one on a single host for testing purposes, you don't need to specify those numbers. The defaults are fine. So then you can, I'm sorry I don't have an example. I should have included an example of what these commands look like, but they're basically the first things you want to do are table add, and you give a table name from your P4 program. You give the keys that are specified in your P4 program for that table, either in hex or it'll take dotted IPv4 decimal notation for IPv4 addresses and a few other special things, but hex always works with 0x. And then you give a table, the action name, sorry, each table you can specify one or more actions. You specify which action you want, any packet that matches that key that you just specified. Give an action name, and then you give the parameters for that action. So you can do table add once, twice, 100 times through the Simple Switch CLI, and it'll all get communicated over this TCP socket to the Simple Switch process. It'll add those to its in-memory tables. All right. So now you're ready to send and receive packets and see if your program works or doesn't. I'm always very pleasantly surprised when my program works the first time, not just in P4, but in just about any programming language. So let's see. Once you've got all these things running, you've got a few table entries set up. You need some way of generating packets and sending it into one of these virtual Ethernet interfaces. There's multiple choices here. A very nice one, if you're going to be doing sequences of multiple headers in a row, I mean, you can just specify a raw sequence of bytes if you want. That's perfectly fine. It's just tedious. There's an open source library in Python called Scapy. It's a very nice, convenient thing. You can write expressions. Sorry if that's a little bit small, but you can say things, for example, like there's a Python class for generating Ethernet headers, and then in parentheses, it takes optional arguments for each of the headers. The nice thing about them being optional is if you don't care about the value, you just leave the arguments blank, and it will fill in default source MAC and destination MAC addresses for your Ethernet header. It will fill in a default ether type, for example, to say what the next header type is. So in this example here, we see the Ethernet. We have an Ethernet call / an IP header / UDP / payload. And so Scapy has done the appropriate overriding of Python methods and operators so that this will create an Ethernet header followed by an IPv4 header followed by a UDP header followed by the payload with that string, the characters in that string payload. And it will fill in all of the next protocol fields or ether type fields appropriately for you. You don't have to worry about what the numbers are. So it's a very nice library for creating arbitrary header stacks. And then you can also decode them in that form, similar to the way Wireshark can as well. And then there's a command here for just, you constructed a packet, it's just stored in memory, and then you can send it to a particular selected virtual Ethernet interface here. There are other tools for generating packets, of course. You can write your own programs if you want. Scapy is just, I've spent a little time on Scapy because it's a very convenient thing for this. If you're just doing low packet rates, debugging, it's perfect. A lot of flexibility there. On the other side, I mentioned Wireshark earlier. That's definitely one option. Scapy itself, you can also run code in Python that says, please start sniffing on one or more virtual Ethernet interfaces, and then store the copies of packets in memory in the Python process as the packets are captured. And then you can decode them and print them out in various different ways. And again, Wireshark, T-Shark is just a text version of Wireshark. Many other ways to copy packets somewhere else and look at them later. Okay, so we've gotten now through, I think, a whole flow. This would be a nice, 3 hours morning worth of work to download these tools, compile them all, and try this kind of thing out. you could probably do it in less than 3 hours if you're faster than me. So yeah, you can get to your first hello world kind of P4 program in a few hours with the open source tools. The READMEs are pretty nice for installing it. I actually have a GitHub repository. I don't have a link, sorry, in the slides, but my name's Andy Fingerhut. If you look for Fingerhut, there aren't that many people with that name on GitHub, and I've got a P4 guide repository that has maybe a few more cooked up steps for running your first demo P4 program if you'd like. All right. So a couple of other open source tools. Once you've done your first hello world and tried that out, if you actually want to get into more serious development, there's other things that you might want to do. One thing that's built or used by the open source P4 compiler for testing it is a framework called PTF, or the Packet Test Framework. And this is a bit of an eye chart here, sorry, but the basic just give the idea of, it lets you, as I said earlier, you can manually use that CLI process to create, that simple switch CLI process to create table entries you can add. This is just a different syntax for doing the same thing that this PTF framework lets you add table entries before you start sending packets. And then you can send in packets, in this case specified by hex, not SCAPI. And you can also set up what packets you expect to come out. And then given this PTF framework will add all the table entries, generate all the packets to send in, and check the expected, whether the expected packets came out or not. This is really only something you want to use after your hello world and by hand testing is done, and you just have, you think you got something working, and then you want to regression test an existing program over time. This is one way to do it. Other people create other frameworks besides this one, but this one's free. Other tools. So all the stuff we've talked about here so far with Simple Switch has been talking about how to emulate one P4 programmable device and forward packets through it. In a network, of course, you want potentially many, dozens, hundreds of switches in a data center, for example, or a campus network. And in some cases, obviously, you might want to test the interaction of your P4 program. You want to have this device put on some new custom header that you only want in your network, carried across the network to another device, which then interprets that header. So it's nice to be able to have, you can take these tools and definitely run multiple instances of Simple Switch, either on a single machine or on different machines, and then hook them up through these either virtual Ethernets on the same machine or physical Ethernets between different ones, and simulate a network of many switches, all programmed with your program. Mininet is just a nice way of firing up a bunch of these simple switch processes and creating the virtual Ethernet hookups. You can specify a fairly simple configuration file, what you want the interconnection of your network to be, and it will generate that for you. P4 runtime is something that's right now going through, there's a working group, the P4 API working group. Their goal is to create a program-independent API. That is something where if you recompile a P4 program and deploy it on your network, your control plane needs to know about the new set of tables you have, but you don't need to recompile the control plane code in order to be able to send it messages over the network and add table entries and remove table entries. So the P4 runtime API is being defined now for working with, for that capability. So this would be another way, if you're looking at more production deployments, you don't want hacking by hand and adding table entries by hand. You need a more programmatic way to do it. Multiple ways defined, but the P4 runtime API is something that will be, I think, coming into prominence soon as the working group has got a little bit further in defining, and there's already early implementations of that are open source in the P4 API repository. Sorry, it's actually the capital P, capital I repository in the P4 Lang group. So that's coming along. And in fact, if people are interested in control plane kind of work, the working group is actually meeting soon, I think, to start editing and revising their specification. Let's see. So, as I mentioned, all these tools are open source. Here's the GitHub group P4 Lang that you can go to and find all these repositories. The main ones that I've demonstrated today are P4C, the P4 compiler, behavioral model with a hyphen in the middle of it for the simple switch emulator. And there's a host of others, but those two are the main ones that you'd probably want to start with. The P4 compiler already has, besides this BMV2 behavioral model backend, it can also compile and spit out a program for the extended Berkeley packet filter, which is open source Linux kernel packet filter module that you can use to recognize and keep or drop packets on programmable conditions. And again, later speakers will be talking about their tools for their own backends. Every P4 compiler, every backend needs its own custom P4 compiler backend. The open source P4 compiler has been designed to make it easier to, I mean, there's the front end of the compiler, which is compiling parsing the source code, generating intermediate representation, and then from there on, it's custom to the back end. And there's some documentation that's included with the P4C repository explaining some of the internal structure of the compiler and how it's been designed to make it easier for you or anyone that wants to dig into that and write their own back end or even extend the front end of the compiler, add new features if they want. There's also a portable switch architecture group that's now meeting and planning to publish a document. It's basically the externs that were talked about a little bit earlier, defining those for the P416 language. That document should be coming out later this year, basically just defining those counters, meters, other useful stateful objects that are needed to make an interesting program. And there should also be, as part of that work, examples of how to add externs to the open source tools, since we'll need to do that as part of that work. So hopefully we'll have that as a good, if people want to extend even more things in the future, it should be a good example for how you can do that in the future. Okay, I will take a breath there. Anybody have any questions about anything I've talked through there? Otherwise, we'll go on to the next speaker. I may have surprised them a bit because I didn't use my full time, so. I didn't even come with a joke prepared, sorry. All the jokes I can think of are probably not appropriate. How are we doing? I'm also not good at song dance band either. Oh yes, please, go ahead. Yeah, so if I can try to repeat the question, what's the compelling use case for P4? Why are so many people interested in these kinds of things? And no? No? Software-defined networking in general. Let me, yeah. Yeah, so, I mean, traditionally, I mean, I work at Cisco, and Cisco's put out many years of versions worth of lots of forwarding ASICs and software with routing protocols like BGP and OSPF, comes with it. We support it well and, help customers set up their networks and configure them all the time. A lot of times, I think the main reason for this kind of shift in interest now is VMware and have made it, and other similar companies and software products like that, have made it really easy for the server guys in a data center to spin up virtual machines for new applications. I know Amazon has made it easy to spin up virtual machines for workloads. First, as a startup, if you don't want to, have your own physical infrastructure and you want to scale it up overnight, if you're willing to pay for it, they've made that very easy to do. Traditionally, the network side of that has been lagging. People have, that in those kind of dynamic host environments, they say, look, it's so easy now for me to automate spinning up new virtual machines. Why can't my network adapt as quickly as my server environment can? And so software-defined networking has really kind of been just like, okay, make your network operate the way you want it to, not the way somebody else wrote the software for it originally. That's the main. For P4 in particular, one kind of, besides that overall view of why software-defined networking, P4 in particular, there's, that's more, software-defined network is more in the control plane, like how do I set up new tables, how do I add new routing protocols, how do I add new ways of setting up VLANs, things like that. For P4 in particular, there's the packet forwarding time. There's a lot of features when you're getting to performance debugging of a network. Why are my packets getting dropped? Why is that queue so deep? What was in that queue when my packets got dropped? What other applications are competing with the one that my business critical one that I don't know about, and it's hard to debug? P4 can let you change the way your forwarding code works to give you better visibility into, why is my performance so terrible? So that's the overall view of telemetry, that just visibility into performance aspects of your forwarding plane that a lot of people are really attracted to that aspect of it. Other programmability, of course, is nice too. That's just kind of a hot topic, I think, that a lot of folks are wishing they had more of in their hardware today. Thanks. All right.
Hi, I'm going to talk a little bit about our hardware implementation in Barefoot Networks. So we have a nice-looking ASIC, which is programmable and which runs at 6.5 terabit per second. And the BPS and PPS performance is guaranteed as long as you fit your program into this given pool of resources. Yeah, this is the first Ethernet switch with fully programmable pipeline. And it fully supports the P4 program language through a set of compilers and then tool chains and debugging tools. And the programmability comes at no penalty on power or performance or price. So we are pretty proud of the fact. It is using the state-of-the-art chip design. I'm not a chip engineer, but it's a TSMC 16-nanometer technology. And it has 4 pipes, 4 match action pipelines. So the switching and then queuing and packet replication for multicast happening between those pipelines through this traffic manager. The nice thing about this traffic manager is a full of shared packet buffer. So it's not really divided into 4 sections, one for each pipeline.
Please use this pointer here.
Thank you. Yeah, this one's more better. So in one extreme case, if you have a workload or traffic that requires lots of buffers or queues, then between the pipe 0 and pipe 1, then almost entire packet buffer can be allocated for the particular flow between this pipe 1 port and then pipe 0 and pipe 1. And yes, it has 4 match action pipelines, and the architecture looks almost exactly same as the PISA architecture we introduced in the language part. And all compiled programs running at the line rate, which means that this adding the programmability doesn't really degrade the BPS and PPS throughput. It has a large amount of SRAM and TCAM tables that can host up to 1.3 million IP version 4 routes. The memory resources can be used for maybe a little bit smaller number of IP version 6 routes, or you can use the same resource for lots number of connection tracking or accurate tables. It's just up to you how you define your program. And as long as they can fit into the set of resources provided by the 4 pipes, then you can do that. So it has multiple port configurations. You can have 6,500 gig ports, or double number of 50, or quadruple number of 25 gig ports. And for the communication with CPU, it has a Gen 3 PCIe, and also it has a dedicated 100 gig port or MAC channel. So one of the 65 can be used as a dedicated communication for your remote CPU or a set of servers that you want to run something like a virtual network functions. So they can be used for just telemetry or kind of load balancing or any compute processing that you want to perform just right next to the switch. Yes, question? Oh, you are talking about interoperability between just. So the new next generation chip can coexist.
Pardon me, folks. If you could please go to one of the microphones at either side of the auditorium before asking questions, we'd really appreciate that. Thank you.
Yeah, okay. Probably it's better to take the questions after my session. I will try to secure a few minutes over there. I think the yes, but I didn't fully understand the question. Are you talking about whether the multiple previous generation of chips can be composed together to build the bigger fabric, or whether you are just talking about the interoperability between the previous chipset and then the new generation chip? And then if the question is the second one, the answer is definitely yes. Okay. So if you take a look at the 4 different pipes, and again, we have a traffic manager sitting in between, and then each pipe are looking exactly identical to each other. So it has a RX max and ingress pipeline, the match action units, and an egress pipeline, and then transmission max. And it's repeated 4 times. And each MAC has a 1600 gig max for regular data communications. And each of them also has additional max for packet recirculation, which means that the packet has been processed by the pipeline once, can be re-injected into the ingress pipe again. That's what we call our recirculation. And the packet generator, which can be programmed from the control plane so that it can trigger, actually generate the new packets directly from the ingress max. So you can actually generate a packets and then kind of replicate them out as you wish. And also for the dedicated 100 gig CPU communication. So these additional processing doesn't really harm or hog any throughput from the regular data communications. If we take a look at each individual pipe in more detail, again, each match action programming programmable pipeline has a parser at its front and deparser at the end. And the parser basically extracts out the set of headers into the header struct as we defined before. And then they are processed by the ingress match action pipeline. At the same time, the non-original copy of the full packet itself is being also sent to the deparser. So deparser has all the capability to reuse any bits in the original packet. So they are composed together, the processed version of headers and then original packets, they are assembled together to create a new packet to coming out. And then they are fed into the traffic manager. So we mentioned a couple of times that the traffic manager or the queuing system is not part of the programmable pipeline. So the one reason is that there has been no nice programming abstraction for queuing and scheduling so far. So some of our colleagues with MIT researchers came up with something called priority in, first out scheduling framework, and they published the SICOM last year. So that is the first step to make the scheduling part as a part of the programmable pipeline. But still, in that model, what happens is that the match action pipeline is doing most of the computations to determine what happens to the packet in terms of scheduling. And then traffic manager is just executing those actions. So this is going to be, if we have that implementation in the future next generation chipsets, then it will be still kind of interaction between the MAU pipeline and then traffic manager. Actually, this is the end of my slides, but since I have some time, let me cover a little bit more about some interesting primitives provided by the in our Tofino chipset. So I mentioned about the packet generator. So the packet generation can be triggered by some external events, like a port down event. So whenever such event happens, then a new packet is created by the ingress MAC, and then the packet can be sent out to notify the port down event to some other external entities, or the match action pipeline itself can alter its internal state to react to the port down event. So we have this as a kind of fast recovery capability. And then the packet chain can be also triggered based on timer. So you can set the timer and to generate some periodic kind of hello messages. And then we are using the capability to offload the BFD, bidirectional forwarding detection, that used to be implemented in the CPU control plane, and we completely offload it down to the data plane. And you can also use this kind of timer-based mechanism for many other applications if you want. Actually, internally, we're also using that as a way to do kind of periodic garbage collection, for example. So Robert mentioned about the stateful register extern that you can program into the match action pipeline. So you can actually maintain, for example, per flow state, like the timestamp of the last packet of each flow, or the whatever state you want to maintain for each flow or connection can be maintained in the match action pipeline. But in some cases, you may want to clear out the states periodically. Then the packet generator triggered by timer-based can be used to do this kind of periodic updates or the cleanup processing. And what else do we have? And speaking of that stateful register, and in connection to what Andy mentioned about the telemetry, so the first advanced applications we are building in our team is kind of per packet telemetry. So each individual packet may have a very interesting metadata, like the queuing latency, input-output port, and which tables this packet has gone through, and et cetera, et cetera. So those information can be exported out from the switch to give very microscopic per packet telemetry information to the external entities, or whatever network analyzer, et cetera. So you can run some big data processing to learn more about the network, what's exactly happening at the congestion event. You can also detect microbursts, many things that couldn't happen before. But if you think about the telemetry report traffic, and if you just generate such a report for each and every data packet, then basically you are doubling, or maybe more than doubling, the data center traffic amount. So what we have implemented in P4 is using those stateful register to implement some custom balloon filter. So balloon filter is a data structure that you can use to detect some membership, or whether something has happened before or not. So, but we actually implement some custom balloon filter that tracks the state of each flow in a way such that the telemetry report is generated only when interesting event has happened. For example, the input port of this flow has changed, or output port is changed because of the routing changes, or whenever the queuing delay of this flow experiencing non-marginal change compared to the previous one. And whenever such a state change happens, then it can be used to trigger the report messages so that you can drastically reduce the amount of report messages. And so that what enables this balloon filter operation is that the stateful register, and also the Tofino has many ALUs that can be used for the stateful object. So you can do different level of comparisons and updates, and this kind of read, update, and read, check, and update operation all happening in the one clock cycle. So it provides a packet transaction semantics. So whatever update you make on the given packet will be immediately available for the next packet coming in. So this is quite powerful primitive. There are some more interesting stuff, but for the sake of time, let me briefly talk about the tool chains we have. So this is the kind of line rate data plane. Unlike the behavior model that Andy mentioned, it's not possible to look into the behavior of each packet throughout the pipeline for every packet. But what Tofino provides is something called snapshot. So you can register some certain condition you are interested in. For example, the packet has some specific MAC address. Then once the condition is met, then the entire state of the packet, for example, what is the value of each and every header fields and metadata fields, and also which tables are executed for the packet, can be, the snapshot of that information can be created. So you can use that information for debugging. It's pretty powerful. And we also provide a software model, register, and also timing accurate software model of Tofino. It's way slow, so you cannot really run line rate traffic. But using the PTF test framework, you can generate whatever interesting packet you want to see, and then inject into this model. And then the model will execute the program exactly as same as what the hardware will do. And then the model will generate very detailed logging messages. For example, which table is hit, and on which condition, and which action is executed. As a result, how the state changes. So before you run your actual program on the actual hardware, then you can run your program in the software model, and then do lots of debugging, and then make sure it's functional correctness for Tofino, and then move on to the actual hardware. And another set of kind of interesting tool chains are coming with the compiler. So basically, the Tofino is a pool of resources configured in a specific way. And once you have your P4 program, you may want to know if the program fits into the resource constraint, then that's good. But in case it fails, for example, if you're asking for millions of version 4 routing tables at the same time, maybe another millions of connection tracking tables, then it may not fit. Then you may wonder whether you can actually fiddle around in terms of tuning the size of tables, or maybe you can change the program a slightly different way so that it can better fit into the program resource constraints. So the compiler is generating very interesting kind of visualization logs, showing, for example, all the dependency graph between the tables. So when you see that graph, basically you can tell, oh, the table A and table B has a dependency. I didn't intend. So it is something you can easily remove. So then you can go back and remove the dependency, and those two tables can be placed parallel in the same stage without prolonging the stage requirement. There are many things you can play with those visualization and logging tools. Okay, I think I have 1.5 minutes. If you have any questions, feel free to come up and then ask. If not, I will hand it over to, do you have a question? Yes, please.
I'm curious how you handle a multi-tenant environment and keeping various users from interfering with each other when they're trying to control tables across the remote nodes from the management area.
Yeah, that's a great question. If you're just talking about well-known network virtualization, like using VXLAN, then from the P4 program point of view, that's just another VNI. So you can still handle them in a same way. But if you're asking about multiple different P4 programmers, they want to run their own individual programs at the same time on the same target, then that's a problem of modularity in P4. P4 doesn't have it has multiple primitives, like so that you can kind of combine multiple programs in a kind of nice way, but it doesn't have a full support for virtualizing the network resources for concurrently running multiple programs. So there are activities going on. I'm actually contributing to that effort to some degree. One direction is coming up with some new abstraction that better supports such a modular composition of different programs while still guaranteeing hardware performances. Another direction is extending the architecture framework so that multiple programs can be kind of layered each other. So the actual hardware architecture, hardware-driven architecture is the first layer. And then as a maybe baseline programmer, I can put my P4 program and define it as an architecture and expose some of the injection points for the other programmers to inject their programs in. There are multiple discussions going on, and if you have any specific idea, feel free to share with us. Okay, thank you.
Okay. Well, a second. All right. Hello again. I didn't actually introduce myself formally last time. So I'm Robert Halstead. I work at Xilinx in the labs group. It's essentially the research arm of Xilinx. And my efforts in P4 have been going on for the past couple of years, mainly implementing a backend, which is what I'm here to talk about today. This tool that we've implemented for the FPGA is called P4C to SDNet. I'll explain these terms in a minute. But first, before I get into the actual tools, I kind of wanted to give a quick high-level overview of an FPGA for people that might not be familiar with the device in the audience or just want a refresher. On this slide, I have just numbers for an UltraScale Plus device. Our P4 stuff is not limited just to this device. It will generate regular Verilog, and you can put it on pretty much any modern FPGA. This is really just here to give some numbers. And if you were to look at an FPGA from a little bit of a distance, what you'd see is basically a grid of logic cells. And each of these logic cells have, in this case, a 6-input logic gate and a couple flip-flops. And between these logic cells, there will be wires. Some of them will run locally. Other ones will run across the fabric itself. And to program this FPGA to do something interesting, you're basically writing to memory locations on the fabric that tell the wires where to go, tell the logic cells what to do. And if you want to do something different, you just rewrite to these memory locations. And in that sense, these devices have a lot of flexibility. We call them all programmable within Xilinx. Now, looking back, maybe in the early days of FPGAs, they were a lot smaller, and they tended to get a reputation as being glue logic. You'd have your complex system, and you just had something that you messed up in the development phase, and you just needed a small little device to fix it together. But that's no longer the case. That idea crops up every now and then, but with 3.7 million tiles, they're actually large enough to implement complex systems. In my case, since I'm interested in P4, we can implement full end-to-end switches on these chips. And this picture is a little bit deceptive. If you were to actually look at the layout for a modern FPGA, you'd see something like columns of BRAMs or DSP blocks that you can program and use. If you get a little bit more specialized devices, you can get them with ARM cores and our Zinc lines. For networking people, we have 100G Ethernet Macs that are on the chips. We have interfaces to interlocking cores, and then Xilinx offers IP around each of those so that you can use them. But one traditionally area of interest that we have within Xilinx, and somewhat without, is this idea of programmability. Typically, FPGAs were programmed with hardware description languages like Verilog and VHDL. And they have a steep learning curve. But the interest, at least today, is trying to make the FPGA more reachable to a wider audience. So if you look at literature, you'll see things like HLS or our SDX line of tools. And this is really where we see P4 fitting in. Network developers shouldn't have to worry so much about the low-level details of the chip. You should be able to write a program in a high-level language like P4, compile it down, and have a customized FPGA in our case. So how do we do this? Xilinx has been interested in networking for a while, well before I got there, obviously. And in that time, we've explored a number of different packet processing languages. I'm not going to talk about all of them, but I am going to talk about the accumulation of that, which was our SDNet product. And the reason I'm going to talk about this is because it forms the backbone of our P4C to SDNet compiler. And the SDNet environment, it defined its own language. It came about before P4 had come along. We really made it mostly out of necessity. There wasn't any language existing at the time that did what we wanted to do. So you can think of it, they're roughly equivalent, P4 and, in this case, PX. In terms of functionality, there are some design considerations that I'll go over a little bit later, but this is the basic flow. You have a program written in PX. You send it to the SDNet environment. To harness some of the flexibility of the FPGA, you have a lot of knobs that you can turn at this point, and they'll affect things like your resource usage on the chip, latency, throughput. You even have knobs that will let you control a little bit what your control interfaces look like. But after the tools are done compiling through the SDNet environment, you're left with synthesizable Verilog. Now, FPGAs have a little bit of notoriety in terms of getting designs actually onto the board. Synthesis and place and route can take upwards of a few hours. It's not uncommon. So one thing that was built into SDNet was this idea of a microcoded design. We can build a custom components that you only have to synthesize once down onto the FPGA, and then you have a firmware module that you can recompile multiple times and load that onto the device. The flow basically continues. You take this hardware description, you compile it down. It generates a bit stream. You load that onto your FPGA. If you chose to do firmware, you would load that into it. In reality, this path with firmware tends to not be taken, at least by most of the customers that we have. It has a trade-off where it's going to require a lot more resources, and the data plane isn't really something that people at this point have been interested in changing once they have it working the way that they want it to. But that's the high-level overview of how we take a SDNet program and we get it onto the FPGA. Now, where does P4 come into this? So me being a labs researcher, I was much more research focused, whereas SDNet's more of a product, and they have a lot of resources that go into doing that, verification and support teams and that. So early on, when we were looking at P4 as a possible replacement for PX, the decision was made to compile the P4 language and essentially treat PX as another intermediate layer, specifically for the FPGA backend. So if you were to go to Xilinx.com right now and download the SDNet tools, which I believe should be available from the main webpage, you will have not only the SDNet tools, but as of 2017.1, you'll have the P4C to SDNet compiler that you can play around with as well. And it's going to do this. It's going to compile into PX. And this has a couple of nice features. One, we have a path to the FPGA, and we don't have to go through the verification of a new backend or anything like that. Another nice feature about this path is SDNet already had a simulation and a verification environment. So this is all written in software. And it's typically a lot faster to test and debug your designs at this level. It has cycle-accurate simulation, so you can trace your packet as it goes through the pipelines and look at various things. And this is really a reason why most people opt for the straight compilation of their data plane into the FPGA instead of doing a microcoded design, is that you can debug a lot of things before you actually generate your bit stream. Let's see. There are a couple of considerations that have to go into this model. Since P4 and PX are two separate languages, and while they are very similar, there are some key differences. I'm going to take a quick moment to define one term that you shouldn't have to worry about, but for talking about this mapping, it'll be a lot easier, and that is what SDNet means when it generates an engine. An engine in the SDNet terminology is roughly equivalent to the parser and control components inside the P4 language. It's the top-level mapping that users typically interact with, and you write your code inside of these. To give you a relationship, in P4 you have a parser and a control. In SDNet you're going to have a parsing engine, or an editing engine, as we call it. And the difference between these two is a little bit subtle, and it's really easy to think about it if you look at the packet's path through a P4 switch versus an SDNet switch. So in P4, you have your packet, it comes in, and in the parser, logically you are extracting the headers from the payload. So they're treated as two separate things. And then inside your control match action pipelines, you're updating those header fields as you need for your design. And then when you come into the deparser, you basically look at each of these header fields and you say, okay, this one's valid, put it in, this one's valid, put it in, this one's not valid, leave it out. That model can be very resource intensive onto an FPGA. Really what we want to do is stream the packet through and keep the headers and the payload together as much as possible. So when we have a parsing engine, it's really more of the packet comes in, we look at a mapping of the header values and we say, we can read these points. And then when we go to the mappings for the control planes, it's reading these values and updating them. It's a little bit of an academic difference for the parser and the control planes. But when you come to the deparser, things get a lot more complicated because we now have a packet that has a specific order. And depending on how complicated you write your deparser, like if you start moving things around, we have to map this model of headers that are already extracted and being put in versus a stream of packets that were meant to be modified in line. And then we have other obvious considerations that most people would have for this. Find as much parallelism as you can in the design. Tables are typically a spot for this. Actions that don't overlap, things like that. As for an actual mapping, so this is a high-level view of what most P4 switches you've seen, especially today with the V1 model. You have a parser, match action pipeline, deparser. What this would look like in SDNet would be something similar to this. Parsers are already state machines, so we handle those very well. The idea of a match action pipeline is not something that's inherent to the SDNet environment. But we do have lookup engines, which are effectively the same as P4 tables. And we have editing engines, which are updating things as an action statement would do. The only difference is our lookup engines and editing engines are at the same level. So we map them by connecting two of these together. And at this point, you can usually find a lot of parallelism because you don't need an individual editing engine for every single lookup. A lot of table actions in P4 can be done in parallel and then just fed into one editing engine. And then the deparser is pretty much updating the packet only, so we only really need to use an editing engine in that case. Now, the standard switch, as presented on the previous slide, is nice for generalized switch architectures. Where the FPGA really starts to shine is with its flexibility and being able to support other types of architectures. So say you don't need an ingress and egress pipeline. All you really want is a way to look at your packets, do some simple modifications, and send them out. You can easily, on the FPGA, drop one of those match action pipelines. Or maybe you don't even need to update the packet at all. You're really only interested in looking at what's there, collecting data on it, storing that, and sending it somewhere else for processing. So all you really need to do is just read through the header, or read through the packet with just a parser and update things. The FPGA offers flexibility in this. And the last thing that I want to talk about is the extern object. So the extern keyword was something that we were really excited to see make it into P416, because from a language point of view, it's a way for architecture developers to add their own customized functionality. But from an FPGA point of view, there's nothing really stopping us from passing this functionality along to the user. So it's nice if architectures say, yeah, I can do this. Let me give you a way to implement it in a P4 program. But it's even nicer in our point of view to be able to say, if you can define the parameters for your specific logic, we'll give you a way to drop it into the data plane. And this would look something, it's a bit of a different target audience than P4 itself. P4 is kind of aimed at network developers. If you're going to be doing something like this, you are going to have some hardware experience, and you'll have to write your own VHDL or Verilog files. You could use, in theory, HLS tools to do this as well. But what this will do is let you define your own extern. You can call it wherever you want inside the data plane. And when we generate the FPGA fabric, you'll have this gap with location that when you're doing the Vivado synthesis, you can place your own custom code into this pipeline and let that run. These are the only things I wanted to talk about for my portion of this talk. I have about 3 minutes left. I don't know if anybody has questions that they want to ask. There's microphones at the sides. If not, then I don't know if Johann's ready. All right, thank you.
Hello again. So I'm here to talk about another mapping of the P4 language to something called a network flow processor. So if you are a regular hot chips attendee, you would have noticed that there was a presentation, Hot Chips 25, about this concept of a flow processor. You can just Google for Netronome and hot chips, and then you will see the whole slide deck. So I'll just give you a brief overview of it, and again, look at that slide deck for the further details. This is actually a family of devices, and they range from 16 cores to more than 120 cores. Furthermore, each core can do 8 threads. So there's a massive amount of parallelism in these devices. Another aspect is that they have quite flexible network media. You have Ethernet, you have interlaken, you also have PCIe as another type of media. So therefore, you'll see in a moment, these can be put into service and act as network interface cards. Because they have multiple PCIe buses, you can actually use one of these and connect it to multiple sockets. So you may be familiar with the Intel Xeon's Data Direct I/O capability, where via the PCIe bus, you can write through the cache into the DRAM. And by the time your software executes on your x86, the packets would then already be in the cache. So we can take advantage of this for up to a quad-core Xeon system, and actually, or a quad socket, I should say, and write to the 4 individual sockets directly into their cache, into their memory, avoiding any NUMA overheads. In general, although the sum of the IOs is more than 700 gigabit per second, we rate it as a 200 gigabit per second kind of device, because that is what you would typically get out of it for practical applications, which are more like your high-touch applications. People wouldn't typically use this to replace a basic network card or a basic switch that's just an L2, L3 switch, because it would be overkill. But if you have a lot of tables, stateful operations, etc., it can reach these speeds. Furthermore, as far as the memory goes, it's quite flexible as well. It can use DRAM not only for things like packet buffers. Let's say you want to queue packets for a long time. It can use the DRAM for lookup tables or state tables or things like meters. So because of that, you can actually have millions of entries in these tables and basically use it as a very flexible processor in terms of both what you do to the traffic, the code, the behavior there, and also the usage of the memory, the data structures the code refers to can be very flexibly defined. Lastly, you will see here the C programmable run to completion cores. They take up part of the chip. On the bottom and the top, you can see the IOs, the PCIe and the network IOs. But close to the memory, you can see these function accelerators. And what they do is they basically allow you to do fairly complicated operations in a lockless way next to the memory. So you can, for example, fire off an instruction to these function accelerators to say, look up something in a content address memory. And if you don't find it, add it. And that's an atomic operation. Therefore, the many threads that are in operation can, in parallel, go and execute these. And they don't need to lock, do it, unlock. They just fire off these operations. And the function accelerators are then inherently thread safe. So other examples of things you could do with a function accelerator would be perform a metering operation, increment a byte and packet count, do things like add packets to a linked list or a ring or a stack like a LIFO. So it's quite handy concept to go and get a lot of parallelism in your many threads without the overhead of a long delay lock operation, unlock pattern. There's many more things like hardware for encryption, quality of service, etc. That's also on the device. Again, Google Netronome and hot chips, and you get all the details. So we take the device and put it onto a network card to form a SmartNIC. And these are actually very similar to the NICs that you would find in a typical server, in the sense that they 25-watt power, the half-length, half-height form factor, etc. Even as far as the pricing goes, they're very similar to a regular network card. They are different, though, in that they very flexibly programmed by virtue of using the flow processor chip, and they have gigabytes of DRAM as well. So that's important for large lookup tables. Often there's a space-time trade-off, where if you have a large lookup table memory, you can process packets at a faster rate. Or maybe you need it to be stateful, implement, for example, a firewall, something like that, and learn about many connections or flows in the network. You could even use that to implement queuing of packets if you really wanted to, although typically one tries to get the packets in and out fairly quickly of the system. So having a look at the development environment, this is something that actually compiles the P4 code to native code for the flow processor. So there's a variety of options. You can use P414, you can use P416, and just because the device is inherently very flexible, there are few restrictions in terms of the types of constructs we can support. We heard earlier about restrictions in terms of the type of divide operation. Well, this is a processor, so it doesn't really care what you do. There are no limitations really as far as how deep in the packet you can look, or how many tables you can do the lookups in, which actions you can do, because these things are translated to native code for the processor in a fairly straightforward way. We do go via an intermediate representation. The reason for this is that there's some benefits to having an intermediate level there within a file, a description of the program, because that decouples a lot of the tools from the actual language syntax. So for example, using the same intermediate representation, one can support the P414 or P416 syntax. And let's say you want to do your own language, flow-oriented Python or whatever tickles your fancy. You could go and target that same intermediate representation. So there was an intermediate representation standardized at open source SDN.org and called AIR, which we originally implemented. But we are moving now to the intermediate representation coming out of the P4 toolchain, because that seems to have wider industry adoption. You will also see in this flow to build the firmware, the option to have an extension in C that you can connect. So this is very similar to what we heard for the FPGAs, a kind of a way to take your arbitrary logic and connect it in places where P4 cannot do the job yet. This allows you to do additional things. So what could you do with that? You could leverage encryption features on the chip, or maybe there's stateful operations that are not that well supported in the language yet, and then you can call into the C code to access the full feature set of the chip. It's actually done in such a way that the P4 work that was done on a packet is available to the C. So P4 will go and extract headers and kind of pass them into some internal representation. That is made available to C via structures. so that P4 doesn't have to go and repeat the parsing that P4 already did. Or also the results of matching are made available to C, so that you can only do whatever you need to do as an add-on. In P414, this is called a primitive function. There's a syntax for that. In P416, this is called an extern, but either way, you can use that. Another item you see here is the runtime interface, where a runtime interface is basically a way to simulate the SDN controller in your development process. And there you can put table entries into a JSON file and say, okay, these need to be loaded when the program starts up. You can later on in the life of the program go and change table entries, also using the JSON format. This is very convenient for development purposes because you don't need to go and write your own SDN controller. But for production usage, there's also an API that can be used that you would then write the other side of in your SDN controller or your other control application. So this is an ongoing effort in the industry to go and standardize such an API. We heard a lot about it in the first section in terms of the issues with using OpenFlow for that. There are some other issues, though, if you go and generate the interface using something like Apache Thrift or Google Protocol buffers. You can easily go and export an interface to a program, but if it's too much tied to the program, then whenever the program changes, of course, all your control software needs to also be modified. So there's a value to be had in having a more generic interface rather than a generated interface, which is slightly at a more abstract level. Things that you may be familiar with from other programming languages like runtime type identification and introspection come up there, that you can have the interface in terms of the functions you call be the same, but things like the actual data structures that you want to interact with are queried over the interface, or then manipulated using that more generic interface. So this is a regular NIC, so it can attach to 10, 25, up to 100 gig networks. It could be multiple ports, but there are also, it being a network card, the virtual ports that sit in the server that basically represent your virtual machines. Could be kernel mode, user mode, in other words, DPDK. Could be just the host without virtual machines. And I just represented in P4 as another type of port. And then there's an integrated development environment that can be used to work with this, where you can edit P4 code with syntax highlighting. If you compile it, it will tell you where the errors are. But you can even debug at the P4 level. We'll see in a moment examples of how that works. So there's another flow emerging for this usage of NICs in servers, which goes via eBPF. For those that don't know, eBPF is something in the Linux kernel, which is effectively another kind of a virtual processor. I'll not use the word virtual machine because that's got a different connotation these days, but it's a virtual processor with its own little instruction set, registers, memory operations like maps can be accessed, call outs to helper functions, and so on. And the bytecode for this processor gets loaded into the Linux kernel. It is then with a just-in-time compiler translated into instructions for example, an x86 server. But we actually developed another just-in-time compilation target, that it can target the flow processor. So that is also then available as a workflow to use the P4 eBPF. There's a number of them actually out there, done by various instances. The most complete one currently was done by VMware. And because we just implement eBPF, that can then run the P4 on the SmartNIC via eBPF. So here's an example of the development environment. As you can see on the left, there's a P4 program with, this is now the 14 version, with syntax highlighting of the code. Then next across, you can see the graphical view, where from the P4 program, it will generate a visualization showing you the parse tree. In this case, it's fairly simple, but if it were more complicated, it could go quite big. Similarly, you can visualize your control flow between your ingress or your egress pipeline. You can also click on those graphical elements. So if you click on something there, it'll take you to the line of code where that operation is implemented in your code. And then finally, to the right, you can see the P4 debugging, where you can set breakpoints at the P4 construct level. So if you set a breakpoint on a parser, then when it goes and parses that type of traffic, let's say you put a breakpoint on IP, then it'll break when there's an IP packet received. If you put breakpoints on tables, they look up related, or actions when the actions are executed. You can also see the actual packet flowing through the system, decoded, how it matches tables, etc. So it's fairly handy to be able to debug at the P4 level the code. So in terms of the actual architecture of the data path, there's not a lot to be said here because it's such a straightforward mapping to the actual flow processor. The flow processor, as we've heard, has a lot of threads that operate in a run-to-completion manner. There's special hardware in the chip that will go and load balance packets to the threads. Then a thread would go and pass information, do matching, do actions, fairly straightforward mapping to your program. We do some special things like we can learn about every flow in the network and be very stateful. And because of that, we can also go and cache the results of matching. So let's say the matching were a lot of tables that you want to look up. You can save those lookups and only do one lookup by using the cache concept. The extensions in C are also put into the run-to-completion data path. Now, these are executed on threads, and the threads may then process many packets in parallel, and that could cause reordering. So there is another hardware block at egress to go and fix up the order of traffic, and also to go and handle things like quality of service to the right of that reorder block. This is very convenient for languages like P4 because you could support variable runtimes per packet, variable types of control flow, many actions, whatever you want can map fairly straightforwardly to this. So in terms of next steps, we would encourage you to use these SmartNICs because they're so easy to use. You just plug them into a server. You don't need to go and develop special hardware. To go and experiment you could actually use them with pre-programmed data plane software. So there's something called Core NIC available. That's just a regular NIC that you may be familiar with to emulate that. There is software available to offload things like OVS or vRouter. And then on the programming side, P4 with C on its own, eBPF, it's really up to you. Finally here, I'd like to point you to many different open source and standards bodies that are working in this area. The one I maybe want to highlight here is OpenNFP.org, where there's more than 50 different projects listed for people that are doing these kinds of things. There's many other examples of P4 applications, specifically running on NICs. And that's one pointer. You can also get the tools there, get a way to get the cards there. Another little pointer here is to OPNFV, because that is where a bunch of these APIs are also being standardized. Of course, P4.org does most of the things for P4. So any questions? Okay, so the algorithmic TCAM, it says here it's DRAM backed. What that means is that the actual data that you're looking up into is really stored in DRAM, and because of that, you could have very large tables in there. And there are some algorithms built into the chip. So for example, with one instruction, you can say do a longest prefix match, or do a range match, etc. And it will go and use the DRAM with some optimized proprietary way of also using memory on the chip to split the workload and get higher performance, to go and do these lookups of, let's say, an individual column in a table, of an individual field. But there's also then another algorithm that will take the different column results and combine them in order to form a table lookup. Because the general problem we're trying to solve is really many columns can be looked up, and any field in any row can be looked up with a wildcard basis. And that is what this class of algorithm tries to do. There's a lot of literature on these kind of algorithms, so I'll just refer you to that. Anything else? Yeah, please approach the speakers over lunch if you have any further questions. And I'll hand over to the last section's speaker.
Everybody is ready for lunch. I will be brief. I'm ready for lunch. Okay, so I have just a short section here of kind of future directions, what some researchers have been doing with assuming P4 programmable devices exist, and how they can take advantage of them, and then a few words about getting involved here. So this is not, by a long shot, everybody this is just a sample, a small sample of what people are doing with this kind of things, but just to give you a flavor of what some of the work that's being done out there. So NetFPGA is an open source compiler for P4 that targets, I think I'm not sure how many different flavors of FPGAs. It's been used itself as a base for other university research projects and industry research projects. Again, I think I'll mention if any of these are not open source, but you can Google for any of these things and find their project web pages. PISA is, I talked about Simple Switch earlier today, and that it was focused primarily on debugging, and I may have mentioned it's not targeted performance. So there are VMware has an Open vSwitch, which runs packet forwarding code in the hypervisor of servers with many VMs, and has its own kind of configurability. But you have to write it in C or some other language, and if you're trying to tweak the last bit of performance out of that, it can be challenging and time-consuming training-wise to come up with, to get somebody that knows how to tweak that kind of thing performance-wise. So Pisces is a project where the intent is you can write a P4 program to specify how you want the packet forwarding to work. It will convert it into high-performance code that runs on that server in the hypervisor. Let's see. Another interesting direction of these projects is taking things that are traditionally at the application level running in the host and not pushing the entire job down into the packet forwarding code, but at least some interesting piece of it that can offload some of the work that's done. Similar to the way you have NICs that can offload TCP offload or encryption and decryption. This is more of an application-specific kind of offload into a network device. So, for example, NetPaxos is a distributed consensus protocol that is used often in server clusters. Say we have 3 to 5 or so server clusters that all want to keep consistent state with each other. Paxos is a consensus protocol that's fairly chatty. It sends lots of messages between the servers so that they can keep their state consistent with one another. So that if one of them dies, the others can have the consistent state and keep on going with whatever the server application is from that point. So NetPaxos is looking at writing P4 code that would run and help eliminate some of that chattiness in the messages that are passed between the servers so that the servers don't have to handle many repeated messages in that protocol. Netcache is looking at using P4 to help offload a key value store. If you have a collection of servers that are implementing a key value store kind of lookup capability, this would be taking some of that, putting it into network devices, and then having them help answer queries in your network. A couple of projects here related to formal semantics of P4. One of the nice things, one of the intentions when the P4 specs are being written was to, if you look at C, there's a lot of similarity in syntax between P416 and C, but there's also, if you look at the C language specs, there's a lot of undefined behavior. The word undefined and unspecified occurs, hundreds of times in the C language spec. Things that overflow behavior, for example, is not portable across all C compilers, not guaranteed to be portable. In P4, the intent was to make things like overflow wraparound behavior more like Verilog, where it's defined exactly what result you're going to get in all cases. So it becomes much more that and the lack of things like fancy data structures involving needing loops, pointers, malloc-free. Being more limited, it's much more amenable to formal tools for proving correctness of programs or various higher level properties about programs. And these are a couple of projects where they're looking at taking P4 programs, turning them into logical formulas, and then proving properties about those systems. Future research topics. This is just a few things off the top of my head. There's I'm sure you can think of others. P4 tends to be focused on header processing. And so if you want to do things like encryption and decryption, compression, decompression, deep packet inspection, looking for patterns in the payloads, that's something that effectively has been put off in the world of P4 externs, and hardware implementations of things that can go at terabits per second is an open research question that people have some hardware implementations for some of these things, but there's certainly more work that can be done there. Another would be if you want something in at the hypervisor layer, for example, maybe every customer, every virtual machine running on a host might want its own P4 program that's slightly different or maybe completely different than P4 programs running on all the others. Are there good ways to optimize those into, say, some programmable NIC that it can handle all those different programs running side by side without interfering with one another? And then there are high-performance stateful features. When I say stateful, things like that in P4 you have to use the register extern to do. So something where across different packets you need to remember values relating to flows across multiple packets. Doing those things at billions of packets per second can be a challenge to manage that state and not make sure that it's updated properly. A little bit about the P4 language consortium. So you can go to p4.org, of course, and see all of this, but it is There are academic and industry members. There's a slide, on the next slide will be an eye chart of many universities and companies that are involved in this. All the tools I mentioned earlier are open source. Anybody can contribute to them. Contributing to them, I think you do need to be part of an organization that's part of p4.org in order to have your contributions accepted, but it's free to join. Again, the Apache license is very permissive, very friendly for commercial development on top of these things if you want to take them in-house and add to them in a proprietary way as well. Let's see. Yeah, and it's a California nonprofit. I don't know the legal ramifications of that. But. So here's the eye chart. The Barefoot networks, obviously very heavily invested in this, but lots of other companies have come on board. I'm part of Cisco, and we're definitely looking into what the possibilities are for using this for products in the future. And I'm not going to try to read even half of these because there's just way too many. But you can see there's a lot of people interested in these things. All right, this is just a list of folks. I will point out, I'll single out one, at least Nick McEwen. I guess probably a lot of people know you from probably previous Hot Chips presentations he's done and work. He's mentioned one time that sort of the Barefoot and P4 kind of started from at least thinking hard about a interesting student question. Some student questions he comes across are the best food for thought that sometimes turn into very interesting things. Like he was giving a talk and saying, you know, traditionally there's been very fixed function kind of chips that have been in the industry that can go at, you know, billions of terabits per second, and then the programmable devices, the network processors, tend to be a factor of 10 slower. And student questions like, well, why is that? Why can't you make a programmable thing faster? And he didn't obviously answer, I think, the full question during the talk, but during that class, but that was kind of became the seed of a thought that became, yeah, maybe we can do this more efficiently. So I think that is all that we have here. And we'll have, wow, everybody snuck up right behind me here for if you have questions for anybody here on the panel that you'd like to ask now. And so yeah, definitely take a couple questions now. And then if we don't get to it now, we'll be available down here at the foot and during lunch. Thanks.
So I'd like to really say a big thank you to the presenters for putting together this excellent tutorial and for coordinating so well across 4 companies. Yep. We have time for a few questions live here on stage, and then we go into the lunch break. We take a break for just over an hour. We're back at 1:30. Exact start time is 1:35. But we have time for 5 minutes of Q&A, and then if there's more questions, just take the presenters to lunch and then sit next to them, and you can have another hour with them. So thank you.
Yep. Sure.
You don't give us questions. I think we'll turn it around and we'll ask you some questions.
Oh, nice.
So who in the audience here is actually using SDN in your networks, in your organizations? Okay. Who's actually already experimenting with P4? It's probably equal amount of people that were into SDN and P4. Who is using the services of a little company called Google? Okay, you might not know this, but they're actually running the entire WAN on SDN. And many of the other data centers that run many of the cloud things that you might be using are also already using SDN. So you might actually already be users, even though you don't know it yet.